This is another video in my series on alternating current. In this video, I'm going to continue to look at complex power. In this episode, it is fairly lengthy, so I will use 3 videos. This will be the second in our series of 3. You can find this topic in my course entitled Power Analysis in AC Circuits. You can access this and my other courses on my Stan store at this web address. Keeping in mind how we designate phasors in red and non-phasor or non-vector quantities in black, the complex power is described by the voltage times the conjugate of the current. Now, if we want to describe the voltage, current, and impedance, it would be done with the magnitudes of each times the angle of each. So the voltage would be magnitude V times theta V, magnitude I for the current times the angle theta I, and the magnitude of Z at some angle theta Z. Now, if that describes the phasors for the voltage, current, and impedance, then the conjugate of those would be the same magnitudes and the same angles, only the angles would be minus now. So I've described both the phasor notation for voltage, current, and impedance, as well as their conjugates. And I'm going to go through a series of exercises here involving the complex power as well as Ohm's law. Now, complex power, again, I'm just repeating it, is the voltage times the conjugate current. And we know from Ohm's law that the phasor V is given by the phasor I times the phasor Z. We can replace the V in the formula for the complex power. Now we have I, the phasor I times the phasor Z times the conjugate I, and that is equal to, from our previous in the upper right hand corner calculation, if you remember, that any phasor times its conjugate is the square of that magnitude. So S can also be described as I magnitude squared times Z, which is a phasor. Now, Ohm's law is V over Z, which can be described using our description of terms that we started with, that magnitude, or the voltage vector can be the magnitude V times theta V all over magnitude Z times theta Z. And if we bring the calculation forward, in other words, we divide the numerator by the denominator, we can see that that's going to be magnitude V over magnitude Z at an angle of theta V minus theta Z. And that's equal to the phasor I, or the current phasor. Now, if I wanted to find the conjugate of that current phasor using what we just developed there, I would have to take the minus of the angles. Same magnitude, I'm leaving the magnitudes the same, and I'm just taking the minus of the angles, which would be minus theta V minus theta, or let's start again, minus theta V plus theta Z. And I can move that term into the denominator now, and I now have magnitude V times minus V over magnitude Z times the angle minus theta Z, which is V conjugate over Z conjugate. And if we go back to our description for S, which is the complex power, V times conjugate I, that's the same as V times conjugate V over conjugate Z, which we just developed, which is V times conjugate V all over Z, which then would be the magnitude V squared all over conjugate Z.
This video is part of my electrical technical information series. Be sure and stay tuned, as I will also from time to time be reviewing electrical products that in my opinion are worthy of paying attention to. This address will give you access to the supplier of aforementioned products, and it is also the connection to obtain a free copy of my 50-page electrical power crib sheets.